Hello students, welcome to chemistry. I hope you enjoyed the 3 labs of this week. We're learning about acids and bases, and I thought it would be interesting to see an acid and a base mixed with phenolphthalein. So the base we used was sodium hydroxide. It's something I like to use in the classroom, but since we can't be mixing chemicals, I thought you should at least have an opportunity to see a video of what happens. I'm sorry, I'm a little bit uncomfortable. Do you mind if I just slip into something more comfortable? I'll be right back. Ah, that's better. Yes, much better. Okay, so we had 3 labs this week. Those 3 labs are required. If you didn't do the capillary action lab, that's okay, but it was an easy A, so you should have done it. But if not, make sure you do these 3 labs for this week. If they're a little bit late, that's okay, but make sure you turn them in as soon as possible. All right, well, let's begin the opening. Opening. Is MgOH2 an acid or a base? How do you know? Please write a sentence or two telling me how you know. And then last, can you draw the molecule? Let's see if you can do all that. Please pause the video now. Okay, we're back. Is MgOH2 an acid or a base? So let's remember that there's a polyatomic ion that determines if something's a base, and it's called the hydroxide ion. It's 1 oxygen bonded to 1 hydrogen atom. And if you see this polyatomic ion in a chemical formula, you know that that substance is a base. So MgOH2, there it is. Not only do we see OH, but there's 2 of them. We would pronounce that as magnesium hydroxide. We wouldn't say dihydroxide. Yes, there are 2 of them, but magnesium's a metal, so this whole thing is an ionic compound, and you don't use the prefixes di, tri, tetra. You don't use any of those prefixes when you're naming an ionic compound. So this is just called magnesium hydroxide. And if you were to draw it, it would look like this. It looks a little bit like Mickey Mouse wearing earrings. But magnesium's a large atom. That's why I drew it large. And then there's the hydroxide polyatomic ion, and there's 2 of them. So 1 OH attached here and 1 OH attached there. That is what it looks like. So today's lesson is a continuation about acids and bases. Let's remember that an acid is a molecule or ion capable of donating a hydron, which is a proton, or a hydrogen ion that's represented as H+. That means hydrogen with a 1+ charge. And a base donates hydroxide ions in a solution. A hydroxide ion is 1 oxygen bonded to 1 hydrogen and is represented by OH with a negative because it has a charge of 1 negative. So this is what a hydroxide ion looks like. And if you ever see this, you know you have a base. But I've got to tell you, there are some bases that do not have the hydroxide ion in them. So there are some exceptions. But as a general rule, for beginners, if you see this, you know you have a base. And then there might be other things that make it a base as well. All right, so we did the phenolphthalein lab, and we used sodium hydroxide, and this is what it looks like. It's a sodium atom bonded to the hydroxide polyatomic ion. That is what we were using during our lab Monday. You saw what sodium hydroxide does when it comes in contact with phenolphthalein. And I want to talk about the pH scale today. pH stands for potential for hydrogen, and it's basically a scale of things that are very acidic and very basic. Maybe a very strong acid on the top here in red, and a very strong base here, down here in blue and purple. So an example of something that's very, very acidic with a rating of 1 is a sulfuric acid. And lemon juice, you know, that's considered a pretty strong acid with with a pH level of 2. And then vinegar and orange juice have a level of 3, and so on. For the lab that we did Monday, we used sodium hydroxide. That's very, very basic. And that's why we used it. It has a pH level of 14, which means it's a very strong base. So the bases are down here, the acids are up here, and what do you think is in the middle? Neutral things are in the middle. Distilled water has a pH level of 7. That means it's not an acid, it's not a base, it's right in between. If you add a little bit of salt to your water, if it's like the ocean water, that would be a pH of 8. And then if you add baking soda to water or just take the pH level of baking soda, it would be a 9. That's how this chart works, okay? So there's a convenient chart that allows us to see if something's acidic or basic, and we can even assign it a number from 1 to 14, with 7 being absolutely neutral. The understanding of acids and bases have evolved over the years. At first, they just noticed certain chemicals would eat away things. They would give your skin a burn, and they started calling those things acids. And then there was some other chemicals that seemed to be the opposite. They seemed to neutralize acids, and they were called bases. At first, people had no understanding of what caused an acid or a base. They were just able to classify these chemicals by their properties. But in 1883, Arrhenius came up with a model that formally described acids and bases, and it applied in most cases, but not all cases. So another model came in 1923 called the Bronsted-Lowry model, and both models have a different view of what constitutes an acid or a base, but they're both considered good models, and a chemistry student is expected to have a basic understanding of both of those models. Sometimes the 1883 model is the most useful model, and sometimes the 1923 model is a better thing to use. But they're both good. It's not like the Bronsted-Lowry model made the Arrhenius model obsolete. They're both considered good models that describe acids and bases. And that's the end.